Hi, my name is Catherine Nugent, and I am a postdoc at Lowell Observatory. And I recently defended my PhD thesis at the University of Washington on the binary fraction of red supergiants. So today I'd like to talk about that research and what it means for the progenitors of future gravitational wave events. So, as many of us know, most massive OB stars are in binary systems or at least experience some sort of interactions due to a binary companion throughout their lives. And so the percentage of these stars in binary systems is kind of dependent on how close they are, how you're kind of defining interacting. So 30 to 35% are believed to be in very close period kind of interacting systems where actual mass transfer or Roche lobe overflow is occurring. And as the separations increase, the binary fraction increases as well. And so 70% or potentially greater are in gravitationally bound, but maybe less interacting in terms of Roche lobe overflow systems. And so a very large percentage of these unevolved OB stars are in binary systems. However, the question that I have been interested in for the past couple of years is what about when the more massive star is between 8 and 30 solar masses and it evolves into a red supergiant? What happens with the binary fraction at this point? Does it stay constant? Does it decrease a little bit? And kind of what does this mean for the evolution of these stars and then eventually the progenitors to gravitational wave events? So the first question that I wanted to answer was if you have a red supergiant in a binary system with another star, what type of star would the companion be? And I found that red supergiants will preferentially have B-type companions. And this is because stars that are less massive than 2 to 3 solar masses will still be a protostar by the time the more massive star has turned into a red supergiant. And so these OB stars are very massive, as we know, and so they are short-lived. And so by the time one of these stars has turned into a red supergiant, just isn't very long compared to the time it takes, say, a zero point 0.8 solar mass star to even come onto the main sequence. And so assuming kind of normal binary evolution as opposed to fun things like capture or weird dynamical events, red supergiants will preferentially have more massive companions. And stars that are more massive than a B star, so O stars, or evolved stars like Wolf-Rayet stars, red supergiants, yellow supergiants, they're just incredibly rare. And so they could exist in systems with red supergiants, but just due to the fact that the IMF makes having more massive stars being created kind of rare and their short lifetimes, it's just not likely that you're going to see a red supergiant with another red supergiant or with a Wolf-Rayet star, but it could exist, which is why I say red supergiants preferentially have B-type companions. So I kind of went out to try looking for these systems, and the first goal was to come up with a list of candidates photometrically. And so the idea is that red supergiants are, of course, very red, and if their companions are generally B stars, their companions will be quite blue. And so photometrically, a red supergiant with a B star companion will appear differently than just a single red supergiant or, of course, a single B star. And so here we have a spectrum from the Marx models of a red supergiant where you see the nice titanium oxide bands, and just pointing out that, of course, photometrically, they will appear much redder than, say, for example, here is a B star where you see the nice upper Balmer lines at around 4,000 angstroms, showing that it's this hot star. And so if you then look at what the SED, or the spectrum of a red supergiant B star binary, will look like. It is shown in black in this figure. You'll see that the SED is much flatter, that there is much more blue light than you would find in a single red supergiant, and of course, much more red light than you'd see in a single B star. So this means that if you plot what a red supergiant B star binary would look like photometrically on a color plot, they take up a very specific place in a color diagram. So here we have R minus I on the y-axis and U minus B on the x-axis. The Mark's red supergiant models are shown as the red dots where they land. The B star 06 blue models are shown in the blue dots where they land. And then the black region is where you would expect to find red supergiant B star binaries. And if we add data to this plot, obviously it gets a little more complicated. These are actual observations of spectroscopically confirmed red supergiants and B stars in M31 and M33 from the local group galaxy survey. And then the triangle in red is where we would expect to find red supergiant B star binaries. So these are basically where we have red supergiants with kind of an excess upturn in the blue. And so I then took a list of candidates of red supergiants that fell within this region in color space and red supergiants that had this kind of excess flux in the blue and went and observed them spectroscopically. And I focused on the local group galaxies of M31, M33, and the small and large Magellanic Clouds, because those galaxies we are able to get a complete population of red supergiants down to some limiting luminosity of around a log L of 4. And so I found over 250 new red supergiant B star binaries in these galaxies. This is a very many factor increase from the around a dozen that we were confident we knew about before I started this research. All of those were located in our own galaxy. And here is the spectrum of one of them. So you see the bomber lines from the B star kind of blown up in the region in blue and then larger in the figure on the right. And then the titanium oxide bands from the red supergiant showing that this is a red supergiant B star binary. And so overall, I was also able to determine the red supergiant binary fraction, and I found that it did range depending on host environment. There was a correlation with metallicity where it decreased with decreasing metallicity, whether this points to a causation that metallicity is causing the decrease or whether it is something else such as star formation, history, or other fun things is still an open question. But it is important to note that I did see some sort of change in the binary fraction with environment, and that these results align quite nicely with complementary research being done by Ricardo Dorda and Lee Patrick in the Magellanic Clouds. So one question this kind of brings up, and that is important and kind of one of the main takeaway points that I'd like for this talk, is that if the OB star binary fraction is large, greater than 70%, then why is the red supergiant binary fraction so much smaller? I mean, 15 to 40%. Are these probing the same populations? Is there some sort of effect we're not taking into account? And so one thing I'd really like to point out is just kind of thinking about the evolution of these systems. And so I have my dog and my cat to help me make this point further. And so if you have, say, an OB star binary system where the more massive star evolves into a red supergiant, it'll start off in something like this, where you have a B star and a brand new red supergiant kind of close by it. As the red supergiant gradually, or I guess quickly expands, there you go, then the two stars will become closer and closer together. And so you'll have a red supergiant right next to the B star. As the red supergiant expands some more, then they will grow closer together and interactions might occur. And so you might have Roche overflow between the two systems. If the distance between the two stars is small, on the order of hundreds of solar radii, then a merger will occur and the red supergiant will consume its B star companion. And so you'll be left with what appears to be a single red supergiant. And so the point I'm trying to make is that mergers are very important to the evolution of these stars and are really going to decrease the binary fraction when you get to the red supergiant phase. And here is this plot from Sonnet et al. That shows that at least for O stars, we think that O stars themselves, if they're in very close systems with a binary companion, will merge. And then a large number of them will experience envelope stripping or common envelope evolution, which implies that they're also quite close to a companion. And so when you get to the red supergiant phase, a lot of these, this like around 50% that you see, that doesn't merge but still experiences some sort of interactions, these will merge at the red supergiant phase. And so mergers really bring down the binary fraction and thus kind of change the number of compact object companions in binary systems that you will expect to find that could become gravitational wave events. And so just kind of walking through this in a different way and kind of driving home the idea that mergers are important. So if you start out with two OB stars in a binary system, if they're very close, then at this point, you could have a merger occur. If they are slightly further away, then the more massive one, if it's between 8 to 30 solar masses, will turn into a red supergiant, and you'll be left with the systems that I just talked about, where you have a red supergiant with some sort of OB star companion. If these two systems are within a couple hundred AU, then a merger will occur here. If they're not, then this is where it kind of gets more interesting for gravitational wave progenitor systems. The red supergiant will turn into a compact object, most likely a neutron star, potentially a black hole, and you're left with this OB star in a binary system with a compact object. At that point, the OB star, if it is between 8 to 30 solar masses, will evolve into a red supergiant, and you get a red supergiant with a compact object companion. Now, these systems are very interesting. They are kind of the direct progenitors to gravitational wave events. Sadly, we don't know as much as we'd like to about them. Kind of trying to study them is difficult for many reasons. One, just the compact object isn't really something that we see spectroscopically or, in the visible wavelengths for photometry. And so trying to find red supergiants with these compact objects companions is difficult. Some work that is being done that is very promising for this is looking at radial velocity variations of red supergiants. And this is work that is being done by Ricardo Dorda and Lee Patrick, kind of very complementary to the work that I've been doing with photometry and single epoch spectroscopy, trying to determine the binary fraction in different environments. But this is also very useful to trying to find red supergiants with these compact object companions. However, I just want to point out that this is very difficult because red supergiants have large separations. If a merger hasn't occurred, that they will have periods on the order of decades. And so you need very high spectral resolution spectroscopy of these systems to get radial velocity variations. And you need information spanning decades to try and get some sort of orbit solution to get a mass. We are able to estimate the number of red supergiants with compact object companions using the binary population and spectral synthesis models, and the current number is around 2%. So lower, but also given that red supergiants are so short-lived, maybe this isn't quite as unexpected. Some future work that I think is going to be very important, and I saw that a bunch of eRosita stuff just recently came out within the last couple of days, but eRosita is going to be great for trying to find red supergiants that are X-ray bright and thus potentially have a compact object companion. And currently we have a lot of information about the number of red supergiants in the local group galaxies, but our spatial resolution in the X-ray is not that great there. So I'm hoping that eRosita can help us with especially the Magellanic Clouds, since we now know hundreds of red supergiants, thousands of them in these galaxies, that hopefully with eRosita we can determine which ones are X-ray bright and thus might have a compact object companion. So some key takeaways from this talk are that in terms of the binaries with red supergiants, they will preferentially have B-type companions when we're talking about stellar companions. We found over 250 new ones in the local group galaxies of M31, M33, and the small and large Magellanic Clouds. The red supergiant binary fraction appears to range depending on environment. This could be a metallicity cause, it could be due to star formation history or many other things, still an open question. And kind of the take home point for this part of the conference is really remembering that mergers play an important role in decreasing the number of potential gravitational wave events for massive star progenitor systems. So we know that OB stars are very commonly in binary systems, but not all of these will kind of make it to the end being in a binary system with two compact objects. So thank you so much. With that, I am happy to answer questions.